The purpose of this presentation is to look at soil health and its relationship to soil moisture. Soil compaction is our greatest indicator of poor soil health. Regarding soil health, we do not understand soil compaction. We've been taught that it is driving heavy equipment over wet ground, that it is the physical degradation of the soil. But until we address the chemical and the biological properties of soil health, we will never address soil compaction. The reason is simple. The root cause of soil compaction is a deficiency in water-soluble calcium. We never measure water-soluble calcium. We measure pH, we measure base saturation, but we never measure water-soluble calcium. Our focus has been on the crop instead of the soil. Soluble calcium, this nutrient, this cation, is the greatest in terms of soil aggregation. 1989 to 2017, USDA gave out $67 billion in crop insurance. 57 billion, or 85% of that, went to two things: drought and flooding. Perhaps our inability to manage water. In the springtime in Kentucky, we take water off. Then we start using irrigation systems in the fall to put water back on, or during the growing season. So we're paying for water twice. We're not managing it. Weather is what's happening above ground. Soil structure is what determines the outcomes below it. A compacted field or a calcium-corrected field can receive the same amount of rainfall with two different outcomes. One, we have drought. The other, we have soil moisture that is moving back into the profile. To validate this, of course, we need numbers. This information comes from a farm in Iowa, the banks of the Sheraton River. 16 acres of alfalfa, established in 2019, 10 acres of corn, and 10 acres of soybeans. Nothing changed except the alfalfa. We used a calcium-based program. It has never had nitrogen, phosphorus, or potassium applied. The corn and the soybean fields, infiltration rates were 1.2 and 2.5 inches per hour, respectively. Consistent with soil survey maps for the area, which say 2.5 to 4.5 for those soil types. Should also be noted that the corn and soybean fields were in their first year out of the USDA CRP program. After 3 years on a water-soluble calcium program, the alfalfa field measured 21 inches per hour. That's more than a lot of our hurricanes would drop in 48 hours. This is a structural transformation of the soil itself. The 740% increase is from the soybean field, a 1,635% increase over the corn field. The Iowa field, let's see if I'm in the right place. The Iowa field were measured with a double ring infiltrometer. A different study from Uniontown, Alabama, gives us data using 48-inch probes. One pasture, same soil, same rainfall, two probes located 60 feet apart. One treated with CaluSolv, one untreated control. That test would be ongoing, but we could not keep the probes on line because of thunderstorms and lightning. One pasture, anyway, across the 3 significant rainfall events during that time period, the treated areas reached 24 inches of infiltration depth each time. The control field reached 20 inches on 2 of the 3 events. Every person in this room is measuring part of this system: groundwater depletion, surface runoff, aquifer decline, nutrient loading in the Gulf. The data exists, the monitoring network exists, but something is missing. The chain must start with fertilizer. NPK ignores soil structure. Ignored soil structure compacts. Compacted soil destroys pore space. Pore space means, destroyed pore space means water runoff. U.S. fresh water is at risk, our surface water. The Ogallala is being mined. The Gulf dead zone. These are not separate crises. They are the same crisis. The lever is the fertilizer program. Change the chemistry and rebuild the soil. Calcium ions carry a positive charge. Soil particles carry a negative charge. Calcium acts as a bridge, pulling particles together into stable aggregates. More pore space means water infiltrates faster, runoff drops, and moisture is held deeper in the profile where plants and aquifers need it. This is not a new discovery, but agriculture, the system, does not focus on soil. It focuses on crop yields. What is new is connecting it directly to fertilizer chemistry. NPK was designed to feed the plant. It was never designed to manage soil structure. Over time, it acidifies, disperses clay, destroys aggregate stability, and collapses pore space. This compaction and runoff is not a weather problem. It's a chemistry and biology problem. Water-soluble calcium flocculates soils. Humates and basalt minerals feed beneficial biology, restoring aggregate structure and reopening pore space. Water infiltrates. Biology returns, and phosphorus and potassium, already bound in the soil, begins to unlock. Sustainable agriculture. NPK feeds the plant. Calcium rebuilds the soil and allows the soil to feed the plant. This is data from the same Iowa farm. No phosphorus or potassium inputs were added for 5 years. Exchangeable rates increased. Total P and K rates also increased, but they are not on this slide. Phosphorus increased 41%. Potassium increased 60%. Cation exchange capacity, the soil's fundamental ability to hold and supply nutrients, increased 18% at its peak. This is what happens when soil biology is restored. Nutrients that were locked in the soil by compaction, acidification, and biology restrictions begin to cycle again. Organic matter and cation exchange capacity are the 2 fundamental indicators of soil capital. Both are trending upward on this farm. The December 2020 peak tells an important story. Organic matter hit 4.3%, CEC hit 17.4%. Potassium spiked to 608 pounds per acre with no potassium inputs. The 2022 dip is equally important. Rainfall that year was 32.5 inches, the lowest of the study period. Organic matter and CEC pulled back under drought stress, but yield held at 4 tons per acre. A soil under stress that still produces is not a fragile soil. It is resilient. In 2022, this farm received less rainfall than it did in 2020, yet yield was doubled, 2 inches less rain, twice the crop. What changed was not the weather. What changed was the soil's ability to capture, hold, and deliver water to the plant. This is the definition of drought resilience. Not a crop that survives dry conditions, but a soil that makes dry conditions irrelevant. This is not a farm. This is a 1-acre residential lot in Bullard, Texas. Same mechanism, different setting. Over 3 years, total water use dropped 68.5%. The water bill fell 51.4%. By year 3, the homeowner had saved over $1,400 on a lawn, not a commercial application. The detail that matters most, rainfall during the CaluSolv years averaged 40.8 inches, lower than the 44.5 inches, which was the average before the program began. This room represents the people who measure, model, and manage moisture at scale. This slide is for you. For water managers, improved soil structure reduces effective demand for irrigation water without new infrastructure. For researchers, fertilizer history is an uncontrolled variable in your models. Where soluble calcium has been applied, soil moisture sensors may read higher retention. For network and data teams, soil amendment history could explain anomalies across monitoring sites. It is a metadata layer worth capturing as sensor coverage expands. For modelers, fertilizer chemistry may be the missing variable in soil moisture models. The Corn Belt covers roughly 900 million acres. The majority of it is under conventional NPK programs. The majority of it is compacted. We have over 2,000 soil analysis since 2010 in our collection, 25 states. Those numbers indicate that this information bears more research. If restoring soil structure with calcium returns even a fraction of that water to the profile, the implications are measurable. Billions of gallons returning to the aquifers instead of loading the Mississippi, the Gulf dead zone, the Ogallala, and other major aquifers. This room is fully aware of what would happen if we move in this direction. None of this requires new infrastructure, no dams, no pipelines, no federal construction projects. Every data point in this presentation came from real farms, real probes, and real rainfall events. What it has not yet had is the scientific framework this room can provide. We have field data. You have monitoring networks, modeling infrastructure, and federal science channels. The logical next step is a replicated, instrumented study that puts fertilizer history on the map as a soil moisture variable. The study does not exist yet. This community is the right place to start building it. If this mechanism holds at scale, it belongs in NRCS, NIDIS, and watershed policies conversations. Thank you.
Thank you very much. We're running slightly off on the schedule by about 5 minutes. So just a heads up, we do still have time for 1 to 2 questions. I'm going to start by asking if there are any questions online, just since they've had to be quiet for a while. So Mike, do we have a question online?
What type of calcium is it pure P? Accompanied with elements such as CaSO4.
The problem that we have found is that calcium is not the same. Dr. William Albrecht talked about free calcium in the 60s, And so what we look at is calcium nitrate. We look at water-soluble calcium. In 1 ton of lime, there's 11 pounds of water-soluble calcium. In 1 ton of gypsum, calcium sulfate, there's 33 pounds of water-soluble calcium. In calcium nitrate, there's 300 pounds of water-soluble calcium. So we use that to flood the soil with those calcium ions and increase flocculation and aggregation.